Hey, Chem 100 students, this is Dr. Ricardo. We're going to do the second part of the Chapter 9 lesson. So this is on stoichiometry, which is uh, analyzing how much product you can make from a certain amount of reactant, or how much reactant is needed to react with a different reactant, or how much product is made whenever another product is made. So you can relate any two reactants, any two products, or a reactant and a product, but you always think of them in pairs, right? You look at one with relation to another. Okay, so if that being said, we're going to do a different kind of calculation this time. We're going to do slightly more difficult ones. Last time we did mole to mole calculation. This time we're going to do mole to mass and mass to mass calculation, where it's really the second one that is the most important because that's realistic. You start with a certain mass of material and you figure out how much mass of product you can make. Okay, so that's the kind of thing that you would do in the lab. All right, so this is example 6 from the notes. What mass of hydrogen can be produced by reacting 6 moles of aluminum with hydrochloric acid? So I give you the balanced overall chemical equation here. If you took a look at it, you would recognize that it's what kind of a reaction. You'd say, I've got a metal with a chemical compound, makes a new chemical compound and a new metal. And you should realize that this is single replacement. The aluminum is going from aluminum in the 0 state to aluminum in the +3 state. I can see that pretty quickly because I can reverse crisscross this 3 back up here, right? And that's what aluminum always goes to, is aluminum typically goes to the +3 state. And what's hydrogen going to? Hydrogen's going from +1, right, which is its normal state, to hydrogen in the 0 state. So aluminum is getting oxidized, losing electrons. Hydrogen is getting reduced. What's happening to the chloride ion? Nothing. Chloride ion is going to turn out to be the spectator ion. Okay? All right, so if we want to do this stoichiometry question, I can either do it in 1 step or 2 steps. So first thing I'll do is I'll cover up the answers over here. And let's go ahead and do this. This, I think, is the last one that we're going to do in 2 steps. Then we're going to get in the habit of just banging them out and doing them all straight across in 1 step. Okay, so the first thing this says is what mass of hydrogen can be produced by reacting 6 moles of aluminum with hydrochloric acid. So I have 6 moles of this, right? So I'm labeling everything. And this is in excess because they don't say anything about it, so I don't worry about it. And they want to know how much hydrogen I can make. And they want to know how much hydrogen I can make in grams. So this is going to be question mark hydrogen in grams, okay, or mass of hydrogen, okay? So that's the difference between those two, okay? So I'll put this back up here. How's that? All right, so this is my starting point. Comes right out of the question, comes from the 6 moles of aluminum, and I'm relating aluminum to hydrogen, so the two coefficients I'm going to need is this 2 and this 3. I don't have to worry about the hydrochloric acid, and I don't have to worry about the aluminum chloride. They don't come into the calculation, okay? This one is used up, this one is created. If they would have asked you how much of this was created, you could calculate it, but they didn't. Okay, so here I go. First step, 6 moles of aluminum, all right? That was given to me right in the question, there it is, 6 moles of aluminum. Okay, multiply by my relationship. My relationship is for every 2 moles of aluminum, I create 3 moles of hydrogen. Okay, so just like we did in the last video, goodbye moles of aluminum, hello moles of hydrogen. Okay, so 3 times 2 is 18. 18 divided by 2 is 9. So I would be able to make 9 moles of hydrogen. Okay. Well, that would be great if they were asking me for moles of hydrogen, but they didn't. They asked me what mass of hydrogen I could make. So mass means grams. All right, so how are we going to do that? Well, next thing we need is we need to go to our periodic table and figure out what's the molar mass of H2. Well, remember, hydrogen is the simplest element. So I grab my periodic table, okay? I take a quick look at it. Let me just make this a little bit bigger for you. Here's the ones that you guys have been using. Okay, and you see that hydrogen has an atomic mass of 1.00794. Hey, we said that's close enough to 1.0. We're always rounding to one place after the decimal. So my mass table is going to be very easy. It's going to be, there's 2 hydrogens based on the formula, multiplied by the mass of each hydrogen, which is 1.0, gives me 2.0. So what is that 2.0? That's 2.0 grams for each mole. That's its molar mass. Okay, so let me make this go backwards a little bit. Make this a little smaller for you. Okay, so that's my molar mass on the side. Let's focus. Make it a little bigger. Autofocus. How's that? Okay, so the second step is take my 9 moles of hydrogen and convert it into grams. So how do we do that? We multiply by the molar mass. This is 2.0 grams, are equivalent to 1 mole, and that's for hydrogen. So that's back from chapter 7. Okay, so 9 times 2 gives me 18. I'll write that down here, 18.0 grams of hydrogen. That's my answer. Okay, so 9 times 2 is 18 divided by 1. Goodbye moles of hydrogen, hello grams of hydrogen. Okay, let's take a look. That's the 2 steps, right? First I get 9 moles, and the second step I multiplied by 2 to get 18 grams. Okay, I'm not going to redo this one, but you could have done that in 1 step. In 1 step, you go first from the moles of aluminum by looking at the balanced equation to the moles of hydrogen. That's our 2 to 3 relationship. For every 2 moles of aluminum that go in, 3 moles of hydrogen come out. And then just keep on going, right? Don't stop. Write down your answer. Keep on going. 1 mole of hydrogen has a mass of 2.0 grams. So that is the molar mass for hydrogen. Okay, so 6 times 3 is 18, times 2 is 36. 36 divided by 2 is 18. Or you could have this 2 cancel with this 2, and it would just be 6 times 3 is 18. Okay, we're going to start doing them this way, guys, really soon. Okay, good. Okay, so the next one is really the meat of this chapter, and that is doing mass to mass calculations based on a certain mass of reactant, how much product can be created, or based on a certain mass of reactant, how much other reactant will react with it. Okay, so let's take a look at this first example. Okay, this is example 7. What mass of carbon dioxide is produced by the complete combustion of 100 grams of pentane? And I give you the formula for pentane. It's C5H12. Now, if we were back in the chemical reactions chapter, which was the last chapter, chapter 8, you would be responsible for knowing this reaction. Complete combustion means the reaction of the food or the fuel. In this case, here's the fuel. You don't want to eat pentane, right? It would taste really bad. It's a gasoline component. Pentane has the formula C5H12, so I'll give that to you. Okay, but you do have to know that this food or fuel is going to react with oxygen to produce carbon dioxide and water as the only 2 products. So you would balance this with an 8 here, a 5 here, a 6 here, and a 1 here. Okay, so take a break yourself and just make sure that you agree that this is balanced. Good. Okay, second thing. In our question up here, what mass of carbon dioxide is produced by the complete combustion of 100 grams of pentane? We know that we have 100 grams of pentane going in on this side. So this is our input, right? And I have it to just 3 significant figures. Nobody says anything about oxygen, so it must be an excess, right? If it's not mentioned, it's an excess. They want to know about the carbon dioxide that comes out. So that's what we're interested in. And they want to know it in grams. Did anybody say anything about the water? No, so we're not interested in it. So we're going to need 2 molar masses. We're going to need the molar mass of the pentane, and we're going to need the molar mass of the carbon dioxide. We don't need it for water or oxygen, so I'm not going to calculate it. Okay, so on the side here, I did the 2 calculations. The molar mass for pentane is the carbon's contribution. Each carbon is worth 12 times 5 of them. That gives you 12 times 5. Where'd the 12 come from? Periodic table, right? 12.0 0.0107 is close enough to 12. So 12 times 5 is 60. We should do this with one place after the decimal. And then hydrogen, you know, is atomic mass of 1.007. That's close enough to 1. And there are 12 of them, so 1 times 12 gives you 12. 60 plus 12 gives you 72. Okay, so that's the first molar mass that we're going to need. Second molar mass that we're going to need is carbon dioxide. Here's the contribution for carbon. 1 times 12, because there's 1 carbon. And then 2 oxygens. Oxygen is very heavy. 2 times 16 gives you 32. 16 and 32 is 44. We're going to do carbon dioxide so often that you're going to have it memorized, right? Carbon dioxide has a molar mass of 44. Okay, I'm going to erase all this stuff. Okay, so what are we relating? We're relating the 100 grams of pentane to how many grams of carbon dioxide we're going to be able to get out at the end. So I'll get some paper and I'll cover up the answer and we'll go through it slowly. Okay, so here we go. I've got 100, right? Point, the 3 significant digits, grams of pentane, C5H12. Okay, all right, need to multiply by something to get me to moles. Okay, I cannot work in grams. Grams is not going to be stoichiometric. So the first step is to get from grams to moles. I need my 72. Turns out that every time I get 72 grams of pentane together, I've got 1 mole of pentane. So I don't have to write the pentane formula over twice. It's for both of them, top and bottom. Okay, if I would get off the superhighway right now, my grams would cancel and I'd be in moles of pentane. Okay, what's the step in the middle? First, I use the periodic table to go from grams to moles, dividing by the molar mass from the periodic table. The second step is to look at the balanced equation. For every 1 mole of pentane that goes in, why am I putting a 1 here? Because there's a 1 there. Why the denominator? I want it to cancel out. If this guy's in the numerator, I need it to cancel out here. I need the moles of pentane to cancel. For every 1 mole of pentane that goes in, wow, this thing is an amplifier. I create 5 moles of carbon dioxide. Okay, if I would get off the superhighway right here, I'd wind up in moles, but I'm not getting off. I'm going to keep going. Okay, make it a little smaller. Good. Okay, last step. Now I'm in moles of carbon dioxide. I need to get to grams of carbon dioxide. So the last step is to use my 44. My 44 is how many grams it takes to make a mole of carbon dioxide. Well, back here, I divided by the molar mass of pentane. Here, I'm going to multiply by it. So you're going to divide on the first step. You're going to multiply on the last step. But let's see if that makes sense. What am I in right here? This is moles of pentane, right? Excuse me, moles of carbon dioxide. Moles of pentane already canceled out. So I'm in moles of carbon dioxide. We know that 1 mole of carbon dioxide is equal to 44.0 grams of carbon dioxide. So mathematically, I'm going to take 100 divided by 72, get the answer. Take that answer, multiply it by 5. Take that answer and multiply it by 44. Alternatively, you could take 100 times 5 times 44, get that answer, and divide the whole thing by 72. Either way, you should get the same result. And here's the result that I got to 3 significant figures. It's 306. Okay, so go check that out. 306 grams of carbon dioxide. Okay, put a box around it, and you should be all set. So I'm going to take the time to punch it in to make sure that we're all on the same page. Okay, so I'll tell you what, I'll go across the top in this case. So 100 times 5, it's going to be 500, times 44. Boom, that's the whole numerator. Take that whole numerator, divide it by 72. The only thing that's not a 1 in the denominator is the 72. Look, right? So there I get 305.55. That rounds to 306. This number only had 3 significant figures going in. So this number should come out with 3. Okay, good. Okay, next one. Let's take a look at the second example. This is example number 8. Okay, just cover everything up. How many grams of nitric acid are required to produce 8.75 grams of dinitrogen monoxide according to the following equation? So there's the balanced chemical equation. Okay. So 4 zinc plus 10 nitric acids make 4 zinc nitrates, 1 dinitrogen oxide, and 5 water molecules. So we're relating nitric acid, right? How many grams of nitric acid are required to make 8.75 grams of dinitrogen oxide? So we're relating this material to this material. The difference between this question and the last one is that they gave you the amount of the product that was created and asked you how much of a certain reactant was needed to create it. It makes no difference in the calculation. Okay, you're going to do everything exactly the same way. You're going to say to yourself, how many grams of this do I have? Going to convert that to moles. You're going to look at the balanced equation and relate the coefficients. For every one of these that was created, there must have originally been 10 of these. So we're going to wind up dividing by 10. So it's a 1 to 10 relationship. You got to put a lot of nitric acid in to get a little bit of dinitrogen oxide. So not very fruitful, right? You got to dump a lot of one thing in just to get a little bit of the thing that you're interested in. Okay, we're going to need 2 molecular masses. You don't need it for zinc. You don't need it for zinc nitrate. You don't need it for water. Nobody asked you about them, so don't calculate them. Here's the molar mass for nitric acid. Nitric acid has 1 hydrogen, so 1 times 1. It's got 1 nitrogen, so 1 times 14. That 14 comes right off the periodic table. And it's got 3 oxygens. 3 times 16, because the 16 comes off the periodic table for oxygen. So 48, 14, and 1 adds up to 63. Take 63 grams of nitric acid to make a mole of nitric acid. So we're going to need that in a few minutes. Okay, here's our other molar mass in this little corner up here. Okay, very simple molecule. Nitrogen weighs 14 right off the periodic table, times 2 gives you 28. Oxygen, there's only 1 oxygen, 1 times 16. 28 and 16 is also 44. So it just happens to have the same molar mass as carbon dioxide. Okay, here we go. All right, what are we going to start with? If I read the question, they only give me one number, so that's my way in. It's 8.75 grams of N2O. Okay, so here we go. First set of brackets. I can't work directly in moles. It is not true that 10 grams of this makes 1 gram of that. What is true is that 10 moles of this makes 1 mole of that. So the first step is to get to moles. How do I get to moles? I need my 44, right? And I always divide by it. 44 grams make 1 mole for that substance. Okay, N2O. Goodbye grams. Grams was in the denominator to cancel out. If I would take my 8.75 divided by 44, I'd get the moles of N2O, dinitrogen oxide. Okay, right now I'm in moles of dinitrogen oxide. Keep going. The middle step. First you go from grams to moles. Then you go from moles of one substance to moles of another. Here they are. There's my 2 substances. For every 1 mole of N2O that comes out, there must have been, wow, 10 moles of nitric acid. Got to dump a lot of nitric acid in just to get a little N2O. Goodbye moles of N2O. So what was my motivation? I always put the thing that I want to get to in the numerator and the one that I want to get rid of in the denominator. So that's why it cancels over here. If I would put an equal sign here and do the math, I'd be left with moles of nitric acid. But that's not what they want. They want grams, right? So the last step is multiply by the molar mass of nitric acid, which we calculated back here. That's the 63. Okay, it's going to go in the numerator. 63.0 grams to make 1 mole of HNO3. Goodbye, moles of HNO3. Hello, grams of HNO3. So here we go. 8.75 divided by 44, hit equals, times 10, hit equals, times 63, hit equals, and that'll give you your answer. Other way to do it, go across the top. This guy's in the numerator, 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 numerator. So do all the numerators. 8.75 times 1 times 10 times 63, hit equals, divided by 44, divided by 1, divided by 1. Don't waste your time dividing by 1. That doesn't change anything. Either way. Okay, so this time I'm going to go straight across and show you that it works. Okay, so let's put this up here and put this down here and see if you agree. Okay, so 8.75. As long as I hit equals in between, I should be okay. Divided by 44. Okay. That 0.1988 is right when I get to here. Okay, did that part. Times 10. Hit equals. Times 63. Hit equals. Okay. I get 125.2 is the raw answer, but it may have too many significant digits. 125.28, so I'll write that down just for a second. 125.28 grams of nitric acid. Okay, so what's wrong with that? This guy only had 3. I can't get to 5. That's crazy. So I have to round this so that it only has 3. I have to stop at 125. So 125 grams nitric acid. Good. That's the perfect answer. I've got the number to the right number of significant figures. I got the unit, and I have the substance. Good. Okay, let's see if I got it right. Did. Good. There's number 10. Okay, I'm going to make one more question before we discuss the next topic, which is on limiting reagents. So this one I'm going to want to go ahead and get something that I need from lab to show you this particular example that I have. So I'm going to hold off on that one, and let's make up one more question for you guys to work on. Okay, so this is going to be a stoichiometry question, a non-limiting reagent question, so you don't have to figure out which substance you're going to run out of, because it's never going to come up. Okay. Later on, we'll show you how to do the harder ones, which are called the limiting reagent questions. Okay. So here goes one more non-limiting reagent mass-to-mass question. Okay. So let's do this reaction, which is called the water-gas reaction. So in the water-gas reaction, you take water gas, right, plus carbon monoxide gas. Okay, and it's going to react to make carbon dioxide gas and hydrogen. Oops, sorry, this guy had to be a water over here. Okay, H2O. So this is going to make hydrogen gas. So let's make sure that that's balanced. Okay, so guys, this guy is regular H2O. Right, I'll rewrite it over here, H2O. Good. Okay, so got two hydrogens, one carbon, okay? One oxygen, two oxygens. So I think it's balanced the way it is, okay? All right, so here's my question for you. My question for you is, how much hydrogen gas is produced when 50.0 grams of CO2 gas is produced in in the reaction above. Okay, so let's label everything. What did they give us and what are they asking for? You've got your balanced chemical reaction up here. Okay, so 50 grams of this is, you know, what was produced here. Right? How much hydrogen is produced when 50 grams of this is produced? So 50 grams of this is coming out. This is what they're asking you about. So put a question mark, and what do they want to know it in? They want to know it in grams. Nobody said anything about how much water went in or how much carbon dioxide went in. You don't need to know that, okay? Obviously, enough of these went in to produce 50 of this. If 50 of this was produced, how much of this would be produced as the other product? So this is a case of showing you that, hey, you can relate any two products just like you can relate any two reactants or a reactant and a product. So this is our first example of two products. So what? Okay, so what's the first thing that I write down? I write down my 50.0 grams of carbon dioxide because that's what they gave me in the question. Okay, all right. Remember, grams are not stoichiometric, right? So I need to get from grams to moles. I can only look at the balanced chemical equation when I'm in moles. So to get from grams to moles, we secretly remember that carbon dioxide has a molar mass equal to 44, right? Remember that? And hydrogen, you can see it, each H is worth 1 times 2. The molar mass of hydrogen is just 2.0. It's very light stuff, 2.0 grams per mole. So this is hydrogen's molar mass, and this is carbon dioxide's molar mass. Okay. All right, so which one I'm going to use first? They gave me carbon dioxide. To get from moles, to get 2 moles from grams, I always divide. This is 44 grams, make 1 mole. And who's that for? Carbon dioxide. Okay, what's the step in the middle? I take grams, I get to moles by dividing by the molar mass, then I look at the balanced chemical equation. Okay, sorry I had the error up here, but this is a 1, this is a 1, this is a 1, and this is a 1. So all the coefficients are 1. So for every 1 mole of carbon dioxide that went in, that came out, why it came out? It's a product. 1 mole of hydrogen also came out. Okay, where did that come from? 1 to 1, 1 to 1. Last step. I'm in moles now, and I want to get to grams. I multiply by the molar mass of hydrogen, which is 2.0, to do that. Take a look at what happens. Moles of hydrogen cancel, and I'm left with grams of hydrogen. So I'm going to have 50 times 1 times 1 times 2 is going to be 100. 100 divided by 44. Okay, so that should be the only math that I have. 100 divided by 44. Okay, that gives me 2.27. Take a look. The next number is a 27 again, so this is repeating. So it's just going to, I'm going to round this down to 2.27. This guy had 3 significant figures. This guy's got 3 significant figures. So it does have 2 places after the decimal. And last piece, this is in grams, and it's in grams of hydrogen. Okay. So whenever you make 50 grams of hydrogen, you only make 2.27 grams of, whenever you make 50 grams of carbon dioxide, you only make 2.2 grams of hydrogen. Okay. All right. So now this is kind of neat. Let's take a look at this. So we've quantified this now. This is no longer a question mark. We figured out that this number is 2.27 grams, right? So we were able to produce from this chemical reaction 50 grams of this and 2.27 grams of this. So by conservation of mass, how much of these things must have left the face of the earth? How much of these things must have reacted? Well, if this and this were created, an equal amount had to be used up over here. So these two guys together have to be 50 plus 2.27, which is 52.27 grams. Now, I don't know the breakdown. I don't know how much of each, But if I could calculate one of them doing stoichiometry, I could get the other one by difference because I know together they're 52. So let's calculate the amount of carbon dioxide from the 50 grams, okay? And then we can get the water by difference. Or as a check, we can do both of them by stoichiometry, and they both should add back to 52.27. So this analysis that we're doing right now is called conservation of mass, right? So I'm going to rewrite everything nicely, and let's figure out the other two pieces of the puzzle. We know these two. Let's figure out how much of the two original reactants must have gone in. Okay, so if I rewrite my balanced chemical equation, I had water gas plus carbon dioxide gas makes, excuse me, carbon monoxide gas makes carbon dioxide gas plus hydrogen gas. Okay, so this guy is 50.0, because that's what we were originally told. We just calculated. This guy came out to 2.27 grams. We know by conservation of mass, these two have to equal those two. Whatever products go in are equal to the amount that comes out. So we now know that this is 52. Right? Because 50 plus 2 is 52.27 grams. Okay, but I can't tell the breakdown of this yet. Okay, so what am I going to do? Well, let's take this 50 again because we're sure about that number and relate this guy to this guy. Okay, so if I had, we can go through this pretty quickly. If I had 50 grams of CO2, first step, grams is useless. I need to get the moles, right? 1 mole of CO2 is equal to 44.0 grams of CO2. Okay. Now that I'm in moles, let's relate moles of CO2 to moles of CO. For every 1 mole of CO2 that went in, that came out, there must have been 1 mole of CO that went in, carbon monoxide that went in. Okay, we need a molar mass for carbon monoxide, so I'll do that up in this top corner, right? Very simple. The molar mass for carbon dioxide is 12 for carbon plus 16 for oxygen, right? So that's going to give you 28. 28 what? Grams per mole. And I think we've done this before. What's water's molar mass? 18 grams per mole, right? Why? 16 for oxygen plus 1 for each hydrogen, so 16 plus 2 gives you 18. Okay, so we have those two guys now up there. Those are our references, right? They're not part of this question. They come from the periodic table when we do the molar masses. Okay, all right. So we use this guy's, which we had already calculated. He was 44. This guy's 28, his mass. This guy is 18, and this guy was 2, right? The 44 and the 2 we calculated on the last page. Right? Molar masses right from the periodic table. Okay, last step. I'm going to use my 28 here. It's going in the numerator. 1 mole of CO2 weighs 28 grams. Okay, sorry, CO. Okay, so 50 times 1 is still 50. Times 28. Get the answer. Divide that by 44, and you're done. This one didn't change anything. This one didn't change anything. Does everybody see that? First way to do it, go straight across the top. This times this, hit equals, then divide it by 44. Second way to do it, 50 divided by 44, hit equals, and then multiply that result by 28. Either way, you should get the same answer. Okay. So I'm going to go straight across. So straight across is 50 divided by 44, hit equals. That gets me to here. 1 over 1 doesn't change anything. I need to multiply by 28. That answer times 28. Okay, I get 31.8. Okay, so what's the 31.8? That's this number right here. 31.8 grams of this must have reacted with hydrogen, with water to make 50 grams of carbon dioxide and 27 grams. So we could do this one or two ways. I could take my 52.27, subtract off my 31.8, and get the amount of water that must have gone in and trust that I did the math right. Or I can do stoichiometry to get this number, and then we can see that that plus that has to equal to 52.27. So what I think I'm going to do is I'm going to do conservation of mass to get this number, and then we'll do stoichiometry to check it. But you could do it the other way too. Okay, so by conservation of mass, all of the reactants have to equal all of the products. So here's the products. The products are 52.27. The reactants have to be 52.27. So if this one reactant, now guys, this has nothing to do with the coefficients, right? This is just the total in each of the piles. So I can take the total, subtract off 31.8 to get the amount of water. Okay, so I'm saying the amount of water that must have went in, if I did this right, is 20.47 grams. Okay, so just double check, 20.47 plus 31.8 gives me 52.27. Good. All right, but don't believe that. This is grams of CO. All right, now I can take any of these numbers, this one, or this one, and work my way back to the amount of water to make sure that that does come out correct. So this is the one we're trying to check, right? All right. I'm going to go with my original 50 because that's the one I'm sure with. So go back, 50 grams of CO2 times 1 mole of CO2 is always worth 44 grams. So that's always the lead-in step. Okay. What do I do in the middle? First step, go from grams to moles using the periodic table. Second step, look at the balanced equation. For every 1 carbon dioxide that was formed, there must have been 1 water. So this is a 1-to-1 relationship. 1 mole of CO2 came from 1 mole of water. The water goes in the numerator because that's the thing I'm interested in. I'm interested in calculating how much of this must have originally been there. Okay, last step. Here's our magic number for water, 18, right? 16 plus 2 is 18, goes in the numerator. 18 grams make 1 mole for water. All right. Want to go straight across the top this time? 50 times 18 divided by 44. So let's do that. 50 times 18. Okay, that gives you 900 divided by 44. Okay, I get 20.454. So 20.45, take a look, 20.45 grams. Okay, probably one too many significant digits. This guy had 3. This guy should only have 20.45, rounds up to 20.5 grams. Okay, of water. And back here, this guy really had one too many significant digits, right? That only had 3, 3, 3. This one really should be 20.47. It'll round up to 20.5 also. So look, same number, right? This rounds up to 20.5 grams. Here I have my answer, how much water must have originally been there. Make this a little smaller. 20.5, so those two numbers have to match up. So conservation of mass is a check of the stoichiometry. So starting with my 50 grams in this question, we calculated everything. How much of this would also be produced? How much of this was used up? And how much of this was used up? So we did 4 different stoichiometry questions, and we checked them by conservation of mass. The total amount, the total mass of all of the products must be equal to the total mass of all of the reactants. Okay, so this is the product side, this is the reactant side. Okay, so that is an example of everything that you could possibly calculate in a mass-to-mass stoichiometry question. Okay, great. Talk to you soon.